bubble flow or flowing liquid films, for example. So I don't want to spend too much time on this slide because I think I don't need to try to convince you that there are many technical applications of sprays. Sprays are used in combustion engines, for the cooling of hot surface, for the production of powder through the spray drying process, and many other things. I will start directly by presentation of laser-induced fluorescence. In my experiments, laser-induced fluorescence is used in liquids. So the liquid is seeded with a small quantity of a fluorescent dye, and before to be atomized, and the droplets are illuminated with a laser beam with a wavelength that can be easily absorbed by the fluorescence molecules. So the molecules, they get excited, and after some time, a short time, typically a few nanoseconds, these molecules spontaneously emit photons of fluorescence. And since the direction of the photons is completely random, only a few of them actually reach the receiving optics and contribute to the fluorescence signal. So absorption and emission are two electronic transitions, and after them, the fluorescence molecule is left with an excess of vibrational energy that must be released in the form of heat. And this process is called vibrational relaxation, and it is very important for us because it explains that there is a wavelength shift between the absorption and emission spectrum of the fluorescence. That means, in practice, that it is as easy as just using a chromatic filter if we want to block the light scattered by the particle, the light of the laser that is scattered by the molecules, and only keep the signal of fluorescence. But fluorescence is not the only deactivation process. There are several pathways for fluorescence molecules to lose its energy when it is excited. And fluorescence is only one possibility. The molecules, for example, can lose their energy in non-elastic shock with solvent molecules. And this process is called collisional quenching. And to describe this competition between fluorescence and other non-radiative pathways, we introduce what we call the quantum yield of fluorescence. It is the number of photons that are emitted divided by the number of photons absorbed. And for some of fluorescent dyes that we are using in the liquid, the fluorescence quantum yield can be very, very high, even close to 1. The fluorescent signal that is emitted from a small volume, let's say an infinitesimal volume dV, so this fluorescence, the photons, will first traverse the flow and arrive to the detection systems. And here the fluorescent signal that is detected is proportional to the concentration of fluorescence molecules in the volume dV, the laser fluorescence arriving to the measurement volume, and it is also proportional to the solid angle under which the photons are detected. And there is also two parameters, the fluorescence quantum yield I've just presented before, and also the absorption coefficient at the laser wavelengths. These two parameters are likely to depend with the temperature and the chemical composition. So we will start with measurement of temperature. And for the measurement of temperature, I would say that it exists a lot of fluorescent species that are available commercially, but only a few of them are actually sensitive to the temperature significantly so that we can do measurement. Here in this figure, we compare several fluorescent dyes that are dependent on the temperature, and these dyes are easily soluble in water, and they can be also easily excited by a frequency double Nd:YAG laser at a frequency of 532 nanometer. Their behavior is very different. So for some of them, the fluorescence signal increases with the temperature, while for several of them, the signal is decreasing with the temperature. So as I already explained, the fluorescence quantum yield can only decrease with temperature due to the effect of collisional quenching with solvent molecules. But on the other hand, the absorption cross-section can increase or decrease depending on the laser wavelengths. In multi-phase flows, when there is a dispersed phase, so in particular with droplets in sprays, the presence of particles introduce some additional effect for the fluorescence signal. For example, we have the effect of light reflection and refraction at the surface of the droplets. And these optical effects change the distribution of the intensity of the laser, and it also changes the transmission of fluorescence to the receiving optics and the detectors. And if we'd like to take this into account, we would need to do modeling of these optical effects using, for example, geometrical optics or the mid theory. And it turns out, if we are doing a bit of modeling, that the fluorescence signal that is emitted by a droplet increase with the size of the droplet, but is not exactly proportional to the droplet volume. And it is also a function of the droplet position relative to the laser and to the detection optics. And in the practice, this is a problem because in practice, it is not possible to control the position and the size of the droplets in a real spray. So the main challenge for the measurement would be to have some specific strategy of measurements to deal with this issue that we don't control the position and the size of the droplets. The first solution that is commonly used is to detect fluorescence in two spectral bands. And these bands, we assume that they will be roughly influenced in the same manner by the optical effects I mentioned before. So even if we don't know exactly the size and the position of the droplets, normally these parameters could be eliminated by doing an intensity ratio of the fluorescence in these two bands. And to have something that is precise for the measurement of temperature, we need to select bands that have temperature response which is very different. A solution, like in this figure, is to use two fluorescent dyes, to mix two fluorescent dyes that have a very different response to temperature and whose emission spectra are shifted in wavelengths. So in this figure, the peak on the left corresponds to the emission of fluorescein, which is increasing with temperature, while the second peak on the right corresponds to sulfurodiamine 640 and is slightly decreasing with temperature. And by doing the ratio, we obtain something that is in principle independent on the optical effect that we cannot control in a spray. A first example is the measurement that I've done a long time ago, but it's still relevant for this presentation. It is the combustion of fuel droplets in a flame. So the droplets are injected by a piezoelectric droplet generator. All the droplets that are produced have exactly the same size and the same velocity. They are produced periodically. Since they are made of fuel, they are injected into a heated coil, and this is sufficient to ignite the vapor and to form a flame that will envelope the droplet stream. We use two crossing laser beams to induce the fluorescence of the droplets. This arrangement is useful because it makes it easy to do the optical alignment of the receiving optics, and also we can do measurement of the droplet velocity using laser Doppler velocimetry. So the signal from the droplet is first transmitted by an optical filter to a notch, by an optical fiber to a notch filter, which eliminates the light scattered by the droplets at the laser wavelengths. Then for the remaining fluorescence, we use two filters and a dichroic beam splitter to divide the fluorescence signal in the two selected spectral bands. And then after, two photomultipliers convert the light flux of fluorescence into an electrical current, and then after we calculate the intensity ratio. And from this intensity ratio we can derive the temperature. For that we need to have a reference. This reference can be done apart in a cuvette. In a cuvette where we control the temperature and measure it with a thermocouple, for example. And we also need to take a reference. Here, the reference is taken at the outlet of the injector, since we can control with this system the temperature of the liquid that is injected. And in this case of a droplet stream, since the droplets are exactly the same, the injection is periodical, the idea was to implement a scanning approach to reconstruct the temperature field inside the droplets. So the two laser beams, they are focused with a lens that has a short focal length, and this allows to obtain an excitation volume inside the droplet, which is very small in comparison to the droplet volume. And so like that, when a droplet moves in front of the laser beam, it is scanned vertically, and then after we shift laterally the position of the nozzle, the injector, and we scan the droplet along a different line, and so on. We repeat this operation to reconstruct the temperature field inside the droplet. So that's an example of measurements that we obtain for the combustion of ethanol droplets. So these maps, they correspond to different times, and you can see that the temperature is not uniform. The heating of the droplet is faster at the bottom of these temperature maps, which corresponds, in fact, the droplets are moving vertically, so this corresponds to the trailing edge. And what explains that the temperature is not uniform within this droplet is the fact that since the droplets are moving, there are friction of the gas at the droplet surface, which induces some recirculation flow inside the droplets, and this circulation flow modifies the distribution of temperature. So we were able, with this approach, to study the effect of the droplet velocity, the distance between consecutive droplets on this internal temperature transport inside the droplets. So the technique I presented can be also extended to an imagery technique. It is relatively simple. We just need to replace the photomultiplier by cameras. In this system, we just use one objective in front of a beam splitter. There are some variants. We can use one beam splitter and two objective lens in front of the camera, but the result is about the same. In these techniques, we prefer using a pulse laser because it allows us to have a high pulse energy, which is ideal to obtain instantaneous image of the temperature. And in this example, the technique is used to study the impact of droplets onto a heated surface. And we decided to use a sapphire window because like this we can do image from a side view. And at the same time, we can observe the droplets from below using a tilted mirror. So when a droplet impinges onto a very hot surface, a surface at a temperature much higher than the boiling point, the droplet does not touch exactly physically the surface. There is always the formation of a vapor film, and so this is the Leidenfrost effect, and there is a two output for the drop impact. The droplets, they can bounce or they can break up at the impact, and that depends mainly on the Weber number, which compare the kinetic energy of the impact to the surface energy. So here is the first example of image we obtain in the case of a water droplet impinging the sapphire at a temperature of 600 degrees. Both regimes, the bouncing and the flashing regime, are presented. The interaction time, the contact time between the droplet and the surface is relatively short. It's just a few milliseconds. And it turns out that the heating of the droplet is much more intense in the case of a splashing. But even in this case, if you look to the color scale, the temperature that we obtain is not equal to 100 degrees. We hardly obtain 90 degrees. This is not a problem of measurement. There is no error of measurement. It is just that in this technique, the temperature that we actually measure is a kind of average temperature through the thickness of the liquid film. And this changes a bit the signification of what we observe, and we must take into account this averaging effect when we compare the results to a model. So this is an example of model, a very simple model we have used to compare to this measurement of drop impact. In this model, we assume that the heat is transferred preferentially along the vertical direction, which is perpendicular to the liquid vapor interface. We suppose that the temperature of this interface is equal to the saturation temperature. And for the convective term in the heat equation, we use an asymptotic, an inviscid flow solution that is used by many authors and that describe the flow when there is an expanded liquid film. So we expect this flow is valid inside the thin lamella at the center of the droplets. When we solve this equation, we obtain the following heat flux, and after we can integrate this heat flux over the time and also over the surface of apparent contact between the droplet and the wall. And like this, we have a value for the average temperature of the droplets. So if we do that, we can compare our measurements with the experiment. So we just use the temperature obtained in the measurements, do the average, and compare to the theoretical average that we have from the model. And we do this first for ethanol droplets, and as you can see, it works relatively well for different value of the Weber number. So the model seems to be reliable in that case, but it is not good when we do the same comparison, but in the case of water droplets. in that case, the same model underestimates the droplet heating by a large factor. And in fact, the only solution we find to obtain a good agreement between the model and the measurement was to assume that the temperature at the liquid-vapor interface is not equal to 100 degrees, but is much higher, and we had to assume that the superheating of the liquid could reach about 270 degrees, which is very, very high, but not totally impossible for the thermodynamics, since the spinodal of water, I think, is about 300 degrees, so maybe it is possible to have this. So now that I've presented some measurement of temperature, this measurement I presented, they were obtained in ideal situation. It was a droplet stream, it was individual droplets. But in a spray, the things are much more complicated. There are several problems that are specific to sprays. One of these problems is the multiple light scattering by the droplets. When there are many droplets in a spray, even some droplets that are not exactly on the trajectory of the laser beam can receive some laser light because of the light scattering by neighbors' droplets, and they will emit some fluorescence in return. So if we increase, for example, this is presented in this image, if we increase the injection pressure in a spray, we will have more and more small particles that will scatter light. And what we observe is that fluorescent light is scattered and is present a bit outside of the expected measurement volume. So the effect of this multiple light scattering is that it makes it difficult to have a localized measurement, but it also come with the problem that this multiple light scattering will also induce some background noise, a background noise that is very difficult to remove. But there is even worse than this problem of multiple light scattering. The main problem that we have in a spray is that the detectors that we use to measure the intensity, they have a limited dynamic range. And the intensity of the fluorescence from the droplets increase roughly with the droplets volume. So if we have a spray with large distribution of droplet size, it becomes almost impossible to detect the small droplets because they will be very difficult to distinguish from the background noise, and there are a lot of background noise because of multiple light scattering. And at the same time, measure the big droplet because they will be easily saturated. And because of this, usually all the measurements, they are biased because we missed the small or the big, or both the small and the big droplets of the spray. So because of this, we decided to change completely our approach and to develop a new technique that is not based on the intensity, but on the measurement of the fluorescence lifetime. The fluorescence lifetime corresponds to the times fluorescence molecules remain in the excited state before returning to the ground state. And this can be measured by using some ultra-short laser pulse that can be produced either by a femto or a picosecond laser. So after the excitation by the ultra-short laser pulse, the fluorescence will decrease following an exponential decay. And we need to find the best fit of this decay to obtain the value of tau, the fluorescence lifetime. The advantage of the lifetime, it is an intrinsic property contrary to the intensity. The intensity, if the transmission, the instruments are a little bit perturbed, this will affect the value for the the intensity of the signal, but normally this will not change the lifetime. So for the measurements, the femtosecond laser beam is focalized into the spray, and the emitted fluorescence is transmitted after to a photomultiplier. This photomultiplier is a bit different from the other one I presented before, because this one is very sensitive. It is able to detect single photon. In front of this detector, there is a pass-band filter. It does not affect the measurement. It is just here to remove the light scattered by the droplet at the laser wavelength. What we actually measured in this technique is the time difference between the photon arrival and the reference signal that is obtained by a photodiode that receives directly the laser at the output of the laser. Okay? So the principle of the measurement can be compared to a kind of stopwatch. The timer of the watch is started when there is a laser pulse that is detected by the photodiode, and it is stopped a few nanoseconds later when a photon of fluorescence is detected by the photomultiplier. And the time difference between these two events is recorded into an histogram, and if we repeat the measurement a large number of times, we can obtain the number of photons of fluorescence as a function of time, and this histogram can be analyzed to evaluate the fluorescence lifetime. So we can use this approach to measure the temperature. For example, in water, we can use rhodanine B. The fluorescence decay is faster when we increase the temperature due to collisional quenching. And to describe the effect of the temperature on the lifetime, we can use a kind of Arrhenius law with an activation energy. And there is also one thing that is interesting with using an ultra-short laser. It is that we can we can use some nonlinear effects. A nonlinear effect here is that if we use a femtosecond laser in the infrared, so if we have two photons in the infrared, they can be absorbed at the same time and produce the same effects and a single photon in the visible. This effect is called the two-photon excitation or two-photon absorption, and it occurs preferentially where there is the most intense intensity of laser. So it will take place where the incident laser is focused. And this allows to restrict the fluorescence volume to a very tiny spot of a few tenths of micron, even when there is a very dense spray, where normally with the one photon absorption there is a lot of multiple light scattering. So with this approach, somehow we remove the effect of multiple light scattering. And so this technique, it has been used, for example, to study the mixing of two sprays. It was our validation case. So there is two sprays injected at different temperature, and we move progressively the two-photon excitation spot to scan the mixing region. So this technique is very reliable, it is very robust, but it has a limitation. It is a point-wise measurement, and it took us about, I don't know, maybe 3 hours to reconstruct this image of the temperature. So it is relatively time-consuming, and so we are now trying to work on new techniques to try to be a little bit faster. Now what I've presented, it was only for the temperature, and the idea is also to be able to do the same but for the composition. This would be interested in the case where the droplets are made of several components that, for example, evaporates at different rates. So it's a work that we started a few years ago only. Some fluorescent molecules, they have the properties of having a different absorption and emission spectra depending on the liquid solvent. This is illustrated here in the case of eosin Y. The absorption and emission are shifted depending on the solvent. And for eosin Y, we know the origin of this effect. It is attributed to the solvent polarity. When a molecule of eosin Y is excited, its dipole moment change of orientation, and this induces a reorientation of the solvent molecules in the nearby of these excited molecules. And this process is called what is named solvent relaxation, and it leads to a lower energy for the excited state, so it changes the wavelength of the emission of fluorescence. So for eosin Y, we know about the process. So this phenomenon is in itself, it could be interesting enough to measure the composition, but there is a problem. The problem is that for eosin Y, absorption and emission spectra also depends on the temperature. And for us, it is a concern because when there are droplets that are evaporating, temperature and composition are changing at the same time. So there is a kind of ambiguity if we use the intensity of fluorescence, because we could not distinguish if the variation of intensity would come from the variation of temperature of composition. But at the same time, if we measure the fluorescence lifetime, we observe that it is not dependent on the temperature and retain this strong dependence on the solvent polarity. So we have lifetimes that are multiplied by 4 between water, that is a high polar solvent, and acetone, which is a low polar solvent. And so we use this idea, and to validate the methods, we study the evaporation of droplets in an acoustic levitation. So the droplets, they are levitating thanks to ultrasonic sound wave. So there is an acoustic pressure exerted on the droplets, and this pressure has the effect to counteract the gravity, but at the same time, it changes the shape of the droplets, which are flattened. So the measurement is relatively simple. We use the femtosecond laser. The laser beam is enlarged to eliminate the whole droplet volume. The fluorescence signal is detected by the photomultiplier, and we analyze the fluorescence decay to measure the fluorescence lifetime. And the measurements, they are done in 3 stages, so we need to have a calibration. So this calibration is done separately in a cuvette, so we just progressively add the components of the mixtures to observe the effect on the fluorescence lifetime. And from this calibration, we obtain the evolution of the lifetime as a function of the volume fraction of the components. Then after we carried out the measurement in the acoustic levitator, fluorescence decays are measured at different times during the evaporation process. And these fluorescence decays after are analyzed to obtain the value of the fluorescence lifetime. And these values are converted into a volume fraction using the calibration curve that has been obtained in the first stage. And so here is the first example. It's the measurement of the composition of a pure ethanol droplet. So initially it was a pure ethanol droplet, but since it was placed in a humid air, there was progressively some condensation occurring at the surface of the droplets, which has transformed progressively this droplet of ethanol into a pure water droplet. And this is what we observe here. The red curve corresponds to the volume fraction of water. The black curve is the square diameter of the droplet, and we also have a curve for the water mass inside the droplet. So this we obtain from the observation of the image and the measurement with fluorescence. Unfortunately, it was not possible to start exactly when the droplet is introduced in the levitator because it took us a few tenths of seconds to adjust the optics and everything. But we can see that there is about 3 stages in this process. In the first stage, there is a strong evaporation of ethanol, which induces the condensation of water, and we see that the mass of water is increasing. Then after, the evaporation rate decrease, but the decrease is slow. And this is due to the fact that the water becomes more and more depleted. So yes, it's a phase where ethanol will be depleted at the end. And after that ethanol has been removed, there is just the evaporation of a pure water droplet, which takes place at the slow evaporation rates. So we did that for a different initial composition of the droplets, and what we obtain is that always an ethanol droplet, the droplets will evolve to a pure water droplets. And then after we decided to change a little and to use not ethanol but propanol, which is less volatile than ethanol and about as volatile as water. And we did the same kind of measurements, but in that case we observe that if the initial water content is less than 30%, the droplets evolve toward a mixture in which there is predominantly propanol at the end. But if the initial volume fraction of water is more important, the droplets evolve toward a pure water droplet. So there is a kind of 2 domains of evolution, and this, for us, it was intriguing enough to try to model this phenomena. I will not comment too much of this formula. There are classical formula for the evaporation of droplets. We modified Nusselt-Sherwood number to account for the acoustic streaming, because there is a streaming that is induced by the acoustic field inside an acoustic levitator. We also correct for the change of shape of the droplets, which are not spherical exactly. So, okay, we developed a model that is relatively complete for multi-component droplet, and finally, by adjusting the activity coefficient of the 2 components in the mixture, but we noticed that it is very sensitive, so we had to test several values from the literature before to find the good ones. Finally, we were able, by tuning the chemical activity, to find evolutions that are comparable to our observations in the experiments. And this confirms that effectively it exists several regimes of evaporation towards water or toward a mix of propanol and water. And from this model, we were also able to know what are the parameters that control these attraction domains. These attraction domains, they are controlled by the humidity and the ambient temperature. So my conclusion, I hope that I have convinced you that we can do a lot of things using laser-induced fluorescence to characterize the heat and mass transfer. There are different strategies, different approach, but usually these techniques, they are not, I would say, not direct, they are not straightforward. They need some time to be developed and validated. For relatively simple configuration, like single drops, lines of droplets, intensity methods works very well, but for more complex situation, I think the lifetime could be a good approach and more robust. So that is, and now most of our work is directed to obtain some measurements that are more that have a higher resolution in space and in time. Thank you.
Guillaume, thank you very much for your presentation.
Yes.
A lot of things to do with fluorescence, for sure. If somebody here has a question, feel free. Yeah. Okay.
Thank you.
You can leave the presentation, I guess.
Yes, it's just yes.
There you go.
Because there are several. Okay.
Yes, give it, please.
Thank you for your talk. I'm interesting. Well impressed by your work. I change a little bit the topic. I think a little bit about my application.
Yes.
How this technique would work to measure the temperature field inside liquid film thickness for annular flow?
For any
annular flow inside tubes.
Inside tubes there is this challenge because there is a tube that will deflect the light and probably induce some optical distortion. So if I think there are also some approach, where you can put the tube inside of a medium to do a kind of index matching to a little bit.
Let's think about a square.
Well, yes, this is what I would like to tell you. A circular tube is one thing, but we can do square if it is possible. It's even better. And then after, yes, I think there is no real problem. But as always, the details really count in this kind of measurements. It depends whether you like to be resolved in time, in space, what exactly is the thickness of this film. But normally we have a lot of things, because if it is really thin film, we have this approach that is based on, for example, on 2 photons. And 2 photons, if we use, it could be like using a microscope, that is with the objective touching the edge of the tube. And since the working distances are relatively short, I think we could achieve a microscopic resolution and do measurement in the liquid film thickness. But this, what I am telling you here, it's a kind of pointwise measurement. So if you are interested to have measurements at the same time in all the thickness of the liquid film, then after, yes, it could be more challenging. It is not presented here, but we also, in a thesis a few years ago, studied the temperature inside waving liquid film. The thickness was about 1 millimeter, even less, because of the waves, it was even less than 1 millimeter, and it was possible in that case to use a laser sheet, and by adjusting a bit the inclination of the camera, we were able to do a kind of optical slice inside this film, but then there was a bit of optical reconstruction to account for the effect of the waves that was reflected the light, but it was possible, and we published something about this. So 1 millimeter, I would say that it can be done with intensity-based measurement from maybe a side view, but I'm not sure in your case of the tube. And after we have this microscopic approach with one objective, and we can change the position of the optical window. Something like that.
Okay, thank you.
But of course we have to go into the details, But,
Thank you, Guillaume. Deborah, please.
I will take it to my application. What about if we had like a bulk water or a bulk liquid with bubbles, like in pool wine? What are the challenges?
for boiling, we are starting a bit to work on this, but it's very preliminary work. I think the most challenge for us the idea was to start really from the basic, just one single bubble at one nucleation point, something that we can control. In that case, I think things are doable. There are some challenges. For example, I haven't mentioned here, but some fluorescent dyes, if they are staying too long at a very high temperature, they can, for some time, they can degrade, sometimes not. So we need always with fluorescence to check a little bit. In principle, it is possible, I think, to do things. But usually in boiling, it depends, I don't know. But the difference in temperature between the hot and cold, it depends on if it is just for 2 or 3 degrees of difference between this would be a bit challenging to obtain beautiful image. I think you need to do a kind of boiling where there is some kind of I don't know, times degree of brightness or something like that, if you'd like to obtain something maybe better. It has to be discussed. But yes, boiling is for me a kind of perspective, I would say. And there are several groups in France that are interesting with that, in Toulouse. I have also some contact in Chambéry with a group that would like to study the boiling within a low pressure, boiling at low pressure between 2 glass. So yes, there is effectively things to do with boiling, and we are thinking about this.
Nice.
Thank you. Thank you again. Any other question? I have to make one, Yeah, of course. I have to. I had several, but we'll talk later. But, for the composition measurement, for the calibration, I saw you had a kind of a small pool, and then you were dripping droplets of the other component, I guess.
Yes.
For a moment, I saw you use a polynomial model, but it seems to be a quite high order polynomial.
Yeah, but okay, don't take care about polynomial. Yes, but there is a good question behind. It is why this calibration curve is not like linear or I don't know, and the answer is that we don't know. Because in fact what you have, it's a kind of molecular interaction. There are 2 species, in fact there is 3, there is a fluorescent dyes and 2 solvents. And it is within this kind of molecules, there are some kind of interactions, and they are non-linear, and so it's a bit the same problems that you may have with, I don't know, the saturation pressure. We know that when a mixture is not ideal, the curve can be a bit complicated.
Yeah, that's exactly the question, because you can have an isotropic point, and then the volume of the mixture changes as it's non-ideal. So,
effectively, when we have a mixture of water and ethanol, there is the azeotrope. But since we add progressively, step by step, each component, I would say that we are jumping above the isotrope and the curve is done. But something completely different. Because at the end, when we obtain this measurement, this one, we really say, what happened? Is it an azeotrope? Could we say that we found something like an azeotrope? Because here you see this droplet with an initial composition of 30%. If you limit the measurement to here, the composition stay constant. So you may say, okay, I've just found an azeotrope. And then after, it does not exist. It exists as azeotrope, but for me, an azeotrope is in a boiling flow, in boiling situation. I don't know how to describe this. It is not an azeotrope in the sense that we usually define it. And it turns out after the modeling that it is more because we are slowing the evaporation rate of water because of the humidity, that at the end we can have water and propanol evaporating at the same rate. So it's a kind of artificial. But at the very beginning, I was thinking, oh yes, that's the azeotrope. This is simply the azeotrope, but not. It is not as simple.
Okay. So if there is any other question, okay. So thank you very much. Let's thank again our speaker. Thank you, John. For those online, thank you again. About 10 people watching, so thank you very much. Thank you, guys. Thank you, Leandro.